So here we have a example of a three-phase diagram, and it shows a three-phase graph for both of these substances that are interacting, substance A and substance B. And note that they're not exactly the same graph. What properties of the materials do you think would be the reason why these graphs are not identical? What's different about the materials that you can notice from this graph? Yeah, they might have different masses.
They have different melting and boiling points.
Yeah, it looks like they definitely have different melting points. Substance A looks like it melts at 5 degrees. Actually, that might even be sublimation. It looks like substance A just has two phases. So I would assume that 5 degrees is its sublimation point, whereas substance B melts at about maybe negative 6 degrees and boils around 10 degrees. And also notice that the slopes are different. Do you know what slope represents on a graph like this?
Which slope? Is it the flat line slope or is it the upward slope?
The diagonal, yeah. Okay. Yeah, this is ultimately all about heat capacity. Yeah, exactly. How quickly or how easily a substance warms up. Because if you take a look at the slope of, let's say, this line here, if you think of that as the usual rise over run, on this graph, what quantity is rise and what quantity is run? Yeah, the rise is the change in temperature, and the run, exactly, the change in energy. So the slope is change in temperature over change in energy. Heat capacity, on the other hand, is defined as change in energy over change in temperature. More formally, heat over change in temperature, but in this context, the heat is the change in energy. So the slope is just the exact inverse of the heat capacity. Yeah, I think this was practice quiz number 1. I think it's on Canvas. But yeah, the slope essentially represents the inverse of the heat capacity. So for instance, a large heat capacity would be a very shallow slope. A small heat capacity would be a very steep slope. Steep slope in the sense that you can get a lot of temperature change for only a little bit of energy. Whereas a shallow slope would mean it takes a lot of energy to get a little bit of temperature change. So it's very important to be able to look at graphs like this and be able to deduce some sort of meaning from it. That in any graph of a physical system, if you're graphing some quantity versus some other quantity, it is often the case that the slope has some physical meaning. So anytime you're making a graph comparing two physical quantities, it's a good idea to ask yourself, this change divided by this change, the slope, does that have some physical meaning? Also, not necessarily in this particular case, but it's often a good idea to also take a look at the integral, the area under the curve. For example, if you take a look at, let's say you've got this curve, this function, there's some area enclosed under that. That doesn't always have a physical meaning, but often it does. So it's often a good idea to look at that area. In this case, that would be energy change times the temperature. That doesn't really have a useful meaning in this context that we care about, but it often does have a meaning for other graphs. So those are often very useful things to look at. Anytime you're graphing physical quantities, ask yourself, does the slope or derivative have some physical meaning? And does the integral or area under the curve have some physical meaning? Good things to check anytime you're dealing with a new type of graph. Any questions on that so far? So let's see if we can piece together what's happening here. We have substance A and substance B mixed together, and I think it tells us information about the starting conditions. We know substance A is initially at -5 degrees, so let's mark that on the graph. Substance A begins at -5 degrees, presumably in solid phase. And substance B, let me just mark that as initial. And substance B starts off at gas phase and boiling temperature. So that will be substance B, gas phase, but at the boiling point. So we can mark those initial situations on the graph. And then if we mix these substances together, what would you expect to happen to each one? What changes are going to occur? First of all, would you expect heat to flow? Yeah, B is going to lose energy and A is going to gain that energy. So we're going to get some changes in energy. And why is that? What causes heat to flow in the first place? Why is heat flowing from B to A instead of from A to B? Generally, we expect heat to flow from high temperature to low temperature. And B is currently at a higher temperature, looks like about 10 degrees, whereas A is at -5 degrees. So the hotter substance is going to lose energy, the colder substance will gain energy. And to figure out how much, we can assume that A is gaining energy, presumably along this line, because it doesn't say anything about supercooling or superheating. And meanwhile, B is losing energy along this path. But what can we say about how much energy A gains and how much energy B loses? Yeah, they've got to be the same amount of energy transfer, right? And I wouldn't necessarily say E equals E because we're not saying that the energies are equal, but the changes in energy have to match up. The change in energy from A and the change in energy from B would have to add up to 0. Except for one thing, is this a closed system? No, it tells us that 30 joules are released to the environment. So we actually shouldn't say the changes in energy add up to 0. We should say the changes in energy add up to what? Yeah, -30 because it's a loss of energy. So overall, these changes mostly have to balance out, but there has to be overall a loss of 30 joules. But let's start by assuming that the changes would balance out, except we also lose 30 joules. Do you think it's going to matter if we take that 30 joules from substance A or from substance B or from some from both? Or alternatively, we could try taking away the 30 joules at the end and see what happens. For the moment, let's assume it's a closed system. Which means that the changes in energy have to be equal and opposite, because they've got to add up to 0 if it's a closed system. And that means if A, for example, let's say we're talking about substance A going from the initial situation to the sublimation point. How much energy does it have to gain to make that happen? Yeah, looks like that's 10 joules. So this is A gaining 10 joules. And meanwhile, what happens to substance B? If substance A gains 10 joules, yeah, then substance B would lose 10 joules because they're exchanging energy at equal rates. And of course, they're still not at thermal equilibrium. So we could probably go further than this. Let's do another 10. Actually, it's going to be a while, I think, before they're at thermal equilibrium. For example, for A to completely sublimate would take how much energy? We added 10 joules to make it get up to its melting point, 5 degrees. Yeah, we'd have to add a total of 70 joules, plus 10, and then another plus 60. So let's see if we can, that's a total of 70 joules of energy gain. Let's see if it's possible for B to lose 70 joules, taking it from 160 down to 90. Looks like that's just barely going to make it, right? Because if we take away 70 joules here, bringing it down to 90 joules of energy left. What do you notice about these two substances at that point?
They're starting to get closer to the point of thermoequilibrium.
Yeah, in fact, it looks like if we take away 70 joules from B, yeah, they reach the same temperature. For A, we add 10 and then we add another 60. For B, we subtract 60 and then subtract another 10. That's exactly enough to bring them to the same temperature. So it looks like that suggests that that would be the thermal equilibrium with everything at 5 degrees, B in its liquid phase, and A having just barely reached its complete gaseous phase, just finished sublimating. And if you're not sure how far you can go, you can just do it in like 10 joule intervals. Like substance A gains 10 joules, substance B loses 10 joules. A gains 10 joules, B loses 10 joules. Keep going until they reach the same temperature, one step at a time. So that would be the case if this really was a closed system. Any questions on that so far? So if it was a closed system, sorry, go ahead.
Oh, I'm still a little confused on how you got 60. Just from looking on the graph, it kind of looks like it's at 80, so I'm a little confused.
Oh, in terms of the change. The final value here looks like the final value is 80. But what we're talking about here is how much the change is. So for instance, this change, A raising its temperature up to the melting point requires adding 10 joules of energy. And then after that, sublimating it completely would take 60 joules of energy. Meanwhile, substance B, completely condensing it to a liquid would require removing 60 joules of energy. But we can afford to lose 70 joules of energy if A is gaining 70 joules of energy. So we can deduct another 10 joules, and that turns out to be just enough to bring it down to the same temperature. Or if you're not sure if you can fit the entire jump, you can go one step at a time. So for instance, if you split this up, let's say we didn't know if this was enough yet. What we could do is just go 10 joules at a time, or whatever interval you want to try out. If you just go like 10 joules, and then object B loses 10 joules. And then object A gains 10 joules, and object B loses 10 joules. And keep going one step at a time until they reach the same temperature. At that point, you know they're at thermal equilibrium. But a graph like this that's clearly labeled with all of the energies makes it much easier to just go one step at a time until they meet somewhere at the same temperature. Because same temperature is really the important final situation. Once they're at the same temperature, there's no further reason heat will flow. Any questions on that so far? Yeah, you just go one step at a time, moving along individual intervals. Because the important thing is, ignoring the negative 30, which we're going to have to take into account as well. If it was a closed system, they've got to be exchanging energy at equal rates. The amount of energy A gains must match the amount of energy B loses. So A goes to the right and possibly up, B goes to the left and possibly down, but the amount they go to the left and right have to match. And we keep going until they meet at the same temperature somewhere in between. Once they're the same temperature, there's no further reason for heat to flow because heat flows from hot to cold. If everything's the same temperature, there's no hot and no cold. It's all the same. Any other questions on that as a closed system so far? All right, so let's take a look at what happens if we have to treat this as an open system with 30 joules lost. If we deduct that 30 joules, it probably shouldn't matter when we take away that 30 joules. If we just wait for everything to come to equilibrium and then remove 30 joules to cool everything down a bit more, or if we take 30 joules away at the beginning, it shouldn't matter. Either way, you're just removing 30 joules from the system. So I think it might be easiest to remove 30 joules at the beginning. If we start by saying, let's just take away 30 joules from, let's say, the hotter object, object B. So let's start with that. We deduct 30 joules from object B, which started at 160 joules. This will take it down to 130 joules. So we can treat object B as having only 130 joules of energy. So this is just the minus 30 because it's a closed open system. Let's say loss to the environment. And then from there, after that loss, we can treat it more like a closed system. Beyond this loss, B is losing the energy that A gains. So beyond that point, we can just take this again one step at a time. Let's say B loses 10 joules. Well, let's just go all the way to the end of this segment here. That's how much energy loss. If we just go from where we left off to the end of this bar, completing the phase change, how much energy would that involve? Yeah, that's a loss of 30 more joules. So after we've lost 30 joules to the environment, finishing that phase change would require losing another 30 joules. Can A afford to gain 30 joules while that's happening? In terms of whether we can take it from substance B versus substance A, it ultimately doesn't really matter. We're taking away 30 joules from something. If you had taken away 30 joules from substance A, we could still do the same process. We'd just be starting both of them from a lower point versus both from a higher point. The reason I wouldn't try taking away 30 joules from substance A here is that would take us off the graph. But ultimately, if we had a larger graph, if we had more space over to the left and down, it should still get us to the same result. But yeah, it looks like we can afford to add 30 joules to substance A, because if we add 10 joules to substance A, that brings us up to the sublimation point. Another 20 joules, and we still haven't reached thermal equilibrium. So here's plus 10 plus 20 more. In other words, in total, plus 30. So there's our plus 10, another plus 20. So far we've got everything balanced. Apart from the original 30 joule loss to the environment, B has lost 30 joules, A has gained 30 joules. Let's go another step. We got to be careful here because it looks like if we continue removing energy from B, it's getting close to thermal equilibrium. So let's take this a smaller step. How much energy would B have to lose to reach the same temperature that A is at right now? We're going, looks like from 100 down to 90. So yeah, it looks like B would have to lose, it can only afford to lose another 10 joules. And let's see what happens if A gains. And it's a good idea to maybe start with large jumps because they're not too close yet. But as you get closer to equilibrium, go to smaller and smaller jumps so you can hone in on that equilibrium without accidentally overshooting it. But yeah, let's try, since we just removed 10 joules from substance B, let's try adding 10 joules to substance A. So being more detailed, a smaller jump, that brings it to 50 joules. So adding plus 10 joules. And it looks like they are now at the same final temperature. Everything's at the same final temperature, so that is equilibrium. Looks like everything ends up at 5 degrees Celsius. So we can list this out as the final state. It looks like everything's at 5 degrees. And what can we say about the phase of substance B? Yeah, substance B is all liquid. What about substance A? Yeah, substance A is still on that phase change horizontal bar, so it's in a mixed phase. I would assume probably solid gas in this case rather than solid liquid. Since we only see two phases for substance A, I would assume that represents sublimation, like the way dry ice and carbon dioxide works. It's possible that substance A is three phases. Maybe this is solid, melting, liquid, and then the boiling point is so high it's just not shown on the graph. But presumably this is a transition between either solid and liquid or solid and gas. Also, how much of it would you say is solid versus how much is gas or liquid or whatever it is? Yeah, we can tell. And how can we tell that it's exactly half and half here? How do we know that it's exactly half solid, half gas, and not more of one or the other? Yeah, it's exactly in the middle of this horizontal bar. Because we saw earlier that the horizontal bar was 60 joules of length, 60 joules of energy change. If we've just added 30 joules, it's exactly halfway to the other side. And yeah, if it didn't show numbers, you could approximate it just geometrically based on how far, what percentage of the way over it looks like it is. With this one, though, we've got enough numbers shown that we can be much more precise. We can say it gained 30 joules. It would take 60 joules to get the complete transition. 30 joules is only half of that. So that's halfway changed. So I would say substance A is half solid, half gas, assuming this is a sublimation. Or half solid, half liquid, if this is really the liquid phase and the boiling point is just too high to be shown on the graph. So that's the final state. Any questions on that one? And at this point, I think we can use what we've got to draw an energy interaction diagram, which I think is the second part of the question. For substance A, what types of energy are changing? Yeah, A is gaining thermal energy and gaining bond energy. So we've got E thermal A and E bond A. And what about for substance B? Yeah, substance B is losing bond energy and also losing thermal energy. So each one is changing both thermal energy and bond energy once. And we can list out, for instance, the initial and final temperature of A. We know A starts at -5 degrees, ends at +5 degrees. We know B starts at +10 degrees and ends at +5 degrees. We also know A is gaining mass of the higher energy state. B is losing mass of the higher energy state. And we don't really have masses here, but we could at least say the final mass of the higher energy state is more than or less than the initial state. Also, would you treat this as an open system or a closed system? Yeah, definitely an open system because we're losing that 30 joules to the environment. So I draw that surrounded by a dotted line and with an arrow leaving the bubble saying Q for heat. And then you could also write this out as a conservation of energy equation, delta E thermal A plus delta E bond A plus delta E bond B plus delta E thermal B equals -30 joules, the heat. Any other questions on that one? All right, then let's try out another example that I think will help apply this more numerically. Let me set this up for a moment. All right, so let's say we have a situation where we've got 4 kilograms of ice water slush that's currently half and half. So 2 kilograms liquid, 2 kilograms solid, which of course means it's got to be at what temperature? What's the only temperature where water can be solid and liquid at the same time? Yeah, that's got to be at 0 degrees Celsius, the phase change point. And also, let's say we have 10 kilograms of liquid gold, a very expensive experiment. And we're going to pour the liquid gold into the ice water slush. Let's say the original temperature of the liquid gold is 1200 degrees, which is significantly higher than its melting point. What would be the first thing you'd expect to happen here to each substance? You expose the hot gold to the cold water. Yeah, the gold is going to lose energy and the water will gain energy. And since the gold is currently above its melting point, what type of energy would it be losing? Right, gold is going to lose thermal energy. Meanwhile, the water, which is at its phase change temperature, is going to be gaining bond energy, right? And the big question is, we don't really know how much it's going to change. Maybe the gold loses enough energy to go all the way down to the melting point and start solidifying. Or maybe it doesn't even get that far. Maybe the water heats up all the way to match the gold before the gold completely cools down to its melting point. Meanwhile, maybe the water completely melts and starts to warm up. Or maybe it doesn't completely melt. Maybe it only partly melts. Or maybe it melts and warms up as a liquid all the way to 100 degrees and starts to boil. Maybe it even finishes boiling. We don't know yet. So we can't really draw out a thermal energy or a conservation of energy diagram yet because we don't have enough information at hand. We can find all the information we need from this, but we don't know in advance which changes are happening. We don't know, does the water only change bond energy and then stop? Or does it melt and then gain thermal energy? Does it gain enough thermal energy that it gains more bond energy as it vaporizes? We don't know yet. So one way to check this, to figure out what changes actually occur, is to set up some hypotheticals, some what ifs, some maybes. We know the gold at least starts to cool off. We want to know, does it cool off all the way to what? What would be the next important temperature the gold could reach? Yeah, 1063 degrees, the melting point. So let's check, does the gold actually reach its melting point? And we can write this as a maybe. Let's say maybe the gold reaches 1063. Maybe the gold cools to 1063. Or alternatively, what could be happening to the water? What's the next important thing that the water could finish doing? Maybe the water maybe it completely melts. So let's check both of those maybes and see which one actually happens. The gold cooling off, for instance, that's a change in thermal energy. So we could use our usual formula, MC delta T, mass times specific heat times change in temperature. We've got mass is 10 kilograms of gold. Specific heat of gold, we can look up on the data table. I believe that is, for liquid gold, 0.15 kilojoules per kilogram Kelvin. And we're assuming that the temperature changes by how much? Yeah, minus, well, we want to get from 1200 to 1063. So I think that's going to be 137. Either way, you can just subtract 1063 minus 1200, final minus initial. So that'll be negative 137. And we can write that as kelvins or degrees Celsius. They're interchangeable because we're talking about delta. So 10 times 0.15 times negative 137 is negative 205.5. So that's how much energy the gold has to lose in order to cool down to its melting point, or cool down to its melting point. Meanwhile, the water is gaining bond energy. Maybe it completely melts. That's what we want to find out. We could use our usual delta E bond formula, delta M times delta H. And if we're assuming that this ice water slush completely melts, how much mass is changing phase? We don't have to melt all of it though, because remember, it's already in a mixed phase. It's already half liquid, half solid. Yeah, we just need to melt 2 kilograms. Because this is currently 2 kilograms of ice and 2 kilograms of liquid water. We just need to melt the 2 kilograms that are currently ice. So we can write delta M as 2 kilograms. You can also think of that as final amount of liquid minus initial amount of liquid. We're assuming we end with 4 kilograms of liquid. And we started with 2 kilograms of liquid. So final amount of liquid minus initial amount of liquid is positive 2. And then delta H for water melting is, what was that, 333.5 kilojoules per kilogram. So we get 667 kilojoules. That's how much energy the slush has to gain in order to completely melt. Based on that information, which one of these processes finishes first? Yeah, we can tell the gold cools down all the way to 1063 degrees before the water finishes melting. And how can we tell that? How can we tell that this process finishes first? Yeah, it requires less energy. And you can think of this in absolute value, ignoring the negative sign. Changing energy by 205.5 degrees is going to finish faster than changing energy by 667 kilojoules. Because if this one's losing 205 kilojoules, this one has gained 205 kilojoules, which is not enough to completely melt it. So this one finishes first. The gold cools down all the way to its melting point while the ice is still in the process of melting. So we know this is going to finish, and then it's going to continue losing more energy. If the gold cools down all the way to 1063 degrees and then continues losing more energy, what's going to happen to it? What's the next important change that happens after it cools down? Yeah, it'll start to solidify. We end up going from liquid gold to at least a partially solidified gold. The next big question is there enough energy being lost, contributed to the water? Is there enough energy lost that it completely solidifies? So that's our next big question. Does the gold completely solidify or only partly solidify? So what we want to do here is set up another maybe. We know this one finishes. This one we don't know yet. But let's set up our next hypothetical. We can say maybe the gold completely solidifies. Maybe the gold completely solidifies. That would be a change in bond energy. So we can use the usual delta M, delta H. We're assuming that all of the gold solidifies, so that's all 10 kilograms. Since we're going from liquid to solid, I'll treat this as a negative because we're losing the higher energy state. We end up with less liquid than we started with, specifically 10 kilograms less liquid. And then delta H for gold solidifying is 62.8 kilojoules per kilogram. Multiply those, we get negative 628 kilojoules. So that means it would take a loss of 628 kilojoules of energy to completely solidify the gold. Can the water contribute that much energy? Not quite, because even though 667 is more than 628, the 667 isn't just going to solidify the gold. Right, we need to combine these two processes because the gold is not just solidifying, it's cooling off and solidifying. So if we combine these end up being, what's that, 800 something, 833. It takes negative 833 kilojoules of energy loss to cool off and solidify the gold. And the water melting alone is not enough to cause that to happen. So that tells us that the water will completely melt after the gold cools down and starts solidifying, but before the gold finishes solidifying. So what we have to do here is we have to say the gold does not completely solidify yet. But at this point, as the gold starts to solidify, why is it negative 10 kilograms? If we're talking about the delta M here, generally the delta M is delta M of the higher energy state. In the case of the gold changing from liquid to solid, what's higher energy, liquid or solid? Yeah, the liquid. So that means we want to use mass of the liquid as the indicator. We start with 10 kilograms of liquid. We're assuming we end with no liquid. So final minus initial of liquid would be 0 kilograms of liquid minus the initial amount, 10 kilograms of liquid. So 0 minus 10 becomes negative 10. In general, as long as you're always using the higher energy state as the indicator, any positives or negatives will automatically show up when you subtract final minus initial for delta M. So sometimes they write it as plus or minus absolute value of delta M, but you actually don't need the plus or minus for the absolute value. As long as you're careful to always use final minus initial mass of the higher energy state for delta M, then any positives or negatives will show up naturally. All right, so it looks like the gold has not completely solidified yet, but the water has completely melted and we have extra energy left over. So if the water completely melts and continues gaining more energy, what's the next thing that happens to the water? The liquid water is now going to do what? Yeah, it's going to increase in temperature. And that liquid water might warm up all the way to what possible highest temperature could the liquid water get to? Yeah, could possibly get all the way up to 100 degrees. After that, we're going to have to deal with the phase change again. So let's use 100 degrees as the next goalpost, the next stopping point we want to check. Maybe the water warms up to 100 degrees. That'll be another delta E thermal. So the usual MC delta T. In this case, we're talking about all 4 kilograms of water, because all 4 kilograms is now liquid. So 4 kilograms, a full 4 kilograms, all liquid now, times specific heat of liquid water, which is 4.18 kilojoules per kilogram Kelvin. And the delta temperature, since we're going from 0 to 100, we're adding 100 Kelvins. And again, Celsius and Kelvin are interchangeable as long as you're talking about a delta. So 4 times 4.18 times 100, that's 4 times 418, 16 something. 4 times 418, 1672. So that means it's going to take 1,672 kilojoules of energy to warm up the water from 0 all the way to 100. Is that process going to finish? No, at least not yet. Because remember, the gold is contributing so far. If we're talking about the gold completely solidifying, the gold has contributed 830 something kilojoules of energy. If the water gains 830 something, that's more than enough to completely melt the slush, but not anywhere near enough to also warm it up to 100. So all we can say at this point is that the water has not yet warmed up to 100. It might still, because we haven't finished the process yet. But we can definitely say the gold does completely solidify. Because this much change is way more than enough to cover this much loss. That is, the water, in order to reach 100, which the gold hasn't even cooled off to yet, the water can only reach 100 by gaining way more energy than the loss it takes to cool down and completely solidify the gold. So yes, the gold will cool down and completely solidify long before the water reaches 100 degrees. Any questions on that so far? So at this point, we now have gold that is completely solidified, but still pretty darn hot, combined with water that is now completely liquid. This is finished. We have finished the liquefaction process, but nowhere near enough energy yet to get it to 100 degrees. But now we still have hot gold and comparatively cold liquid water. So they're going to continue exchanging energy. What's the next important temperature that it could get to? Maybe the water warms up to 100 degrees first, or what's the gold doing in the meantime? This now solidified gold. If the gold is completely solidified and continues losing energy, what's the now solid gold going to start doing? Yeah, the gold is going to start cooling off. And now, since the water is warming up, possibly up to 100 degrees, we should check, does the gold cool off to 100 degrees? Which one hits that next important transition first? And we don't really need to worry about any more gold-specific temperatures because gold is not going to go through any more phase change. It's solidified, it can just keep cooling off indefinitely until it matches temperature with the water. So the next big question is, which one reaches 100 degrees first? So let's check another hypothetical. Maybe the solid gold cools off all the way to 100 degrees. And of course, gold specifically doesn't care about 100 degrees. It's not an important temperature for gold, but it's the next important phase change point for water. So we should check which one reaches 100 degrees first. That'll be another delta E thermal. So we can just use MC delta T mass, 10 kilograms. And now we're using specific heat for solid gold, which is 0.126 kilojoules per kilogram Kelvin. And delta temperature, if we're going from 1063 down to 100, that'll be negative 963. As the energy we'd have to lose to get all the way down to 100 degrees. So multiply those together, and we get negative 1,213.4. How does that compare with the energy that the water has to gain? It's less. So it looks like, and of course, really, we should be combining all of these. All the energy lost by the gold. So to get to 100 degrees, we'd have to lose 205 and 628 and 1213.4. So that would cost negative 2,047 kilojoules. Whereas to get the liquid water to 100 degrees, we'd have to add 667 plus an extra 1672. So that's going to require adding these two together, 2,339. So if we look at that in total, which one of these processes finishes first? Yeah, if you look at the total, the amount of energy to cool the gold, solidify it, and cool it further requires a total of losing this much energy. The water melting and warming up all the way to 100 requires a gain of even more energy. So the gold finishes the process first. That is, the gold cools down to 100 degrees before the water gets to 100 degrees. So that means, yes, the gold will finish getting to 100 degrees first. And the water is still not yet at 100 degrees. If the gold has cooled down to 100 degrees and keeps losing energy, it's going to cool off even further. What does that tell us about the final equilibrium temperature? What range could the final equilibrium be in? If we know the gold cools off to 100 and keeps going, yeah, the final temperature is going to be lower than 100. And if the final temperature is lower than 100, what does that guarantee about the water? Yeah, the water is guaranteed to be liquid. We can say not only is this water reaching 100 not yet, we can say this water reaching 100 is never going to happen. We don't have to worry about the water reaching 100 degrees because the gold has already cooled down to 100 degrees and keeps going. And at that point, we know these are all the changes that are going to happen. The gold will cool down to its melting point. The gold will completely solidify. The gold will cool down to 100 degrees and beyond. Meanwhile, the water will completely melt. It will partially warm up, but it won't warm up all the way to 100 degrees. And at this point, now that we know the final state of everything, we will have all liquid water and all solid gold. And we know the final temperature is somewhere between 0 and 100. We just don't know where yet. We can now set up a conservation of energy equation. We can say change in thermal energy of the liquid gold plus change in bond energy of the gold plus change in thermal energy of the solid gold plus change in bond energy of the water melting plus change in thermal energy of the water warming up have to add up to 0. And we can use some of these values. We know that the gold's loss in thermal energy is this much. We can actually use negative 205.5 in our equation. We know the gold loses exactly this much bond energy. We know the water slush gains exactly this much bond energy. We cannot use this one though, because the water doesn't actually reach 100 degrees. And I think we wouldn't want to use this one either, because we know that the gold cools off to 100 degrees and keeps going. So what I would do here is write out those changes. This change exactly as it is, plus this change exactly as they are, plus delta E thermal for water with an unknown final temperature, and delta E thermal for the gold with an unknown final temperature. That way, the only unknown in your equation will be T final for the whole system. It'll show up twice, once for delta T for the water, once for delta T for the gold. But since it's the same T final, you can now solve that equation for T final. And yes, we would make those all add up to 0. All these changes have to add up to 0 because it is a closed system. And why, if the gold cools down to 100, yeah, if the gold has cooled down all the way to 100 before the water reaches 100, they're going to keep changing. The gold is going to continue getting colder than 100. The water will continue getting hotter, but it can't get hotter than the gold. So if the gold has already dropped down to colder than 100, that means the whole system is now colder than 100 degrees. The only way you can get water to boil is to raise it to 100 degrees and keep adding more energy. But in this case, we know the water is not even going to get to 100 degrees. The gold cannot provide enough energy to the water to make that happen. So we know the water is not going to get enough energy to even reach the boiling point, let alone start boiling. Any other questions on that? So in general, this is a really useful approach for any situation where you know you're mixing some substances together, you know their starting temperatures and phases, but you don't know what changes are actually going to happen, and you don't know what final equilibrium is going to look like. Think of it as sort of a race towards equilibrium. Each substance is taking steps towards equilibrium, but you don't know which one's going to get there first. So set up these hypotheticals. For each substance, identify what's the next important transition, the next important critical point it's going to get to. And ask yourself, how much energy would that change require versus how much energy would this other change require? Compare those, or everything you got so far for each substance, to figure out which process finishes first. And then once you know all the processes, once they've met somewhere in the middle, then you can set up an actual energy interaction diagram and conservation of energy equation, because you know what changes are actually happening. Any other questions on that? All right, if you want to get some more practice on this race to equilibrium idea of conservation of energy, go to math.andcheese.org/P7A. It should be a practice worksheet there on similar topics with some explanations. So give that a try, and I will see you next time.